Hello everyone, welcome to CourseSeeded. So today I'll be talking about my research. My name is Shakti Singh. I've posted a research on Zenodo. You can view my research by going on zenodo.org/record/20423633. This is basically my DOI on Zenodo, or you can say on OpenAI. So what you can do is, or you can just go directly to this https://doi.org/this, and you can just see this over there. So this is the link for going to my research. Next, what we have is we can just discuss about the research right now. So we have this research, which is enumeration of bounded circuits using set try filtering. So basically, we are just traveling all the cycles, basically even the non-simple cycles. As you know, in our last lecture, I discussed that we can travel only simple cycles for now with the algorithms that are available currently in the competitive or any C++ program. So I've actually done some research and developed this algorithm for y'all to enumerate all valid cycles in a directed graph, which is basically a fundamental problem in graph theory. So while establishing this algorithm efficiently, what I was thinking is that basically we can take simple cycles and we can also extract non-simple circuits where nodes may repeat but edges are bounded by capacity constraints. So what I mean by that is, suppose you have a graph like this, 1, 2, 3, 1. So suppose if the edge capacity is 2. So by edge capacity, what I mean is you can travel edges k times. You can repeat edges k times, and nodes any number of times while traveling to find a cycle. So what you can do is basically you have this k equals 2. So what you can do is you can travel 1 to 2. So first cycle is obviously 1, 2, 3, and 1. So what the next cycle looks like 2, 3, 1, and 2. And obviously the same way you can just do for 3, 1, 2. But over here, what I want to do is I basically wanted to like travel 1, 2, 3, then going from 1, 2, 3, and then 1. So basically over here we traveled these edges twice, and these edges also twice. So basically we traveled 3 edges twice, but we didn't exceed that limit, and we traveled the nodes any number of times. Basically we traveled 1 3 times, 2 2 times, 3 3 times, 2 times. So nodes can be traversed any number of times, but our edges can be traversed only k times. So this is basically the logic behind what we'll be building. So how can we do that? So at first, you can just write normal code for the infinite loop DFS, and check whether if anything exists and we have already traversed that, then we can exit from there, and then we can continue from the same node from where we exited for the next nodes. So if you want to do like that, then it's well and good, but we'll be using try for the so that we don't get any time limit exceeded error, or you can say we are able to produce the result in minimum time. So at first what we can do is we can produce the lexicographical paths. So why am I producing lexicographical paths? I'll be explaining that to you later, but first let's make the circuits for now. So first let's discuss about the code, what we have written over here. I suppose I've copied it over here now. Okay, so raw circuits are this. Okay, so we are connected to the internet. Let's run this. Okay, so let me just refresh the website. I believe we are getting some internet problem over here. Okay, so yeah, so it's an internet problem. So let's talk about that when the internet comes back. For now, let's discuss what we can do. So first, you know the logic behind what you are doing right now. So second, we have like this was the bottleneck earlier, order of c squared times m, basically the number of edges and the cycles or the capacity, you can say. I mean the cycles, you can say. So this was the number of cycles square times the number of edges. So instead of going through this method, I introduced a method which is called Shakti's algorithm. So basically in this, it's designed specifically to traverse, enumerate, and filter those bounded circuits efficiently. So at first, you should know about Johnson's algorithm, which we discussed in the last lecture. So this was a gold standard for simple cycle enumeration. I don't know why this is happening. Okay, so this was the gold standard for simple cycle enumeration. But the problem was that it took lots of time, and also it wasn't valid for non-simple cycles. So it ignores the non-simple cycles, which was a problem for us. So what we can do is we can basically use the edge tracking method in the depth first search with lexicographical pruning. So with lexicographical pruning, what I mean is, let me just tell you that. So lexicographical, you already know that it's the dictionary type, but the pruning. So pruning means, suppose you are exploring a tree and you have these nodes. So the nodes are 1, 2, 3, and 4. Now suppose you have to backtrack from this to this. Suppose you have got something like 1, 2 over here, then you have 1, 2, 3 over here, and then you have 1, 2, 3, 4 over no, not 1, 2, 3, 4, 3, 4 over here, 2, 3 over here, and you have 4 and suppose 2 over here. You can say 4 and 1. So next, if you are searching for a valid answer, now let's introduce a sample question for this. Suppose you are trying to find combinations of numbers from suppose this is what you're given. These are the nodes or the numbers, you can say, which are given. You have to find the combinations of numbers from this set that adds up to exactly 5. Also, you are given that you can repeat a number if you want, and you must generate them in increasing lexicographical order. So by that, what I mean is 1, 2, and 2 is a valid this combination, but 2, 1, and 1 is not a valid combination because we have to find it lexicographical. You can also write the code which is not in lexicographical, but that will just consume more energy power and CPU for your work. So I have just done the lexicographical thing. So this you have 1, 2, and 2. Next, what you have is there is a possibility that you want to try 1, 2, and 2 and 3. And also if you want, you can also do this. But it all depends on our capacity, which I introduced, that there is a k capacity. So if suppose k is equal to 2, then you can't include this. But if k is equal to 5, if k is greater than equals to 5, then this is obviously a valid combination. But if k is less than 5, then this is not a valid combination. So let's keep the k for now as 2. Let's keep our k 2 for now. So this is not a valid thing. This is not okay. So this is valid and this is valid. So what you can, the idea behind this is, what you can do is your normal algorithm just explores all the paths going from 1, 2, 3, 4. It first checks all these things, then it goes for 1, 2, 3, and 4, and then it might, suppose if you're not using my method, then you might go with the backtracking. Obviously you will go with the backtracking. So what you will be doing is you will be searching for all the algorithms which will be like non-efficient way. You will be like choosing all the possible combinations. So suppose if your k is equal to 2, so what are the possible combinations? I think the possible combinations are 1, 2. Let's just, so like you can choose this 2 times, 2 times, 2 times, and 2 times. So 2 to the power 4, which is equals to 16, right? 2, 4, 8, 16. Yes. So this is like 16 combinations. But if you use my method, then you will be just getting this under like, let me first explain the logic behind my work, then I'll be telling you what the order will be. Basically time complexity. So first we have this. So the logic is we'll be checking, since all are like supposed to be in lexicographical, which is in ascending order or in the dictionary order, order. So what you can do is you can first explore the path, which is 1, 2, 3, 4. Then suppose if you go with the backtracking, so first you'll be going with 1, 2, right? Then you'll be going with 2, 3, 3, 4, 4, 1, and much more. So for first, okay, so this won't be just 2 to the power 4, it will be much more than that. This will be much more than that, but yeah, you'll get what I'm trying to say. So first you have this 1, 2, 2, 3, 3, 4, 4, 1, and 4, 2, 4, 3, and all the other stuff. So basically once you'll travel all this, you'll find that this one is correct. Then what you can do is you can take the same node which you have traversed, then you can just continue from here. So basically 1, 2, and then you can directly go from here to 3. Then you can go from 2, 3 to 4. So suppose if I had to do this problem, then I would be doing it like this. I'll be just creating a cache array, and then I'm storing every cycle in that, and then continuing from there instead of traveling the same cycle twice. So that's what cache method is. So for now we have this 3, 4, which we can go. Okay, so we can also go for 2. We'll also go for 1 and 1, and then we'll go for 1, 2, 2, then 1, 2, 3. Suppose if this goes above, what I want to say is this goes like 1, 2, and then suppose you want to go with 2, 3, or directly with 3. So we won't be continuing this path anymore, because 1 plus 2 plus 3 is greater than what? So it's greater than 5. As you can all clearly see, it's 6. 6 is greater than 5. So we'll be discontinuing this path. So this is the second thing in the code that I would be doing. And I'll be just continuing over here. Since we already got it equal to 5, I won't be continuing anymore from here, because that will also create. So we'll be breaking these two paths as well, but we'll be including them in our answer. Next, what we have is we have 2 and 3 and 4. So basically 2, 3 was valid. So instead of writing all this, I can just say I'll be directly discontinuing this from here. So discontinuation starts directly from here, right? Because this is also equals to 5. So for 3, 4, since it is already greater than 5, so what we can do is we can directly discontinue. And even for 4, 1, we can directly discontinue. Suppose this was like 1, 1. So we can also write 1, 1, 2, 1, 2, and then 1. Or we can just do 1, 1, 1, 2. Okay, so no, this can't be done. Okay, so our capacity was 2, right? So this will be a problem for us. Since our capacity was 2, so we won't be including this because we have 3 ones. So basically we'll never be going to these 3 ones. So this will never encounter this array because our logic is set like that. So we'll be encountering only these two, and or we can encounter this. But suppose if I take 2, 2, then also it will create some problem. So we'll be discontinuing it directly from here. But since we are talking about only 3, so we'll be just going up until this, and all these will be discontinued. So we are only left with one array which can be continued, but this is also a problem because this directly goes 2 plus 6, which is greater than 5. So we'll be discontinuing this too. So instead of going all the way to 1 1 2 2 3 3 4 4 5, okay, so there was no 5. So instead of going all these arrays, we just directly discontinued from the cycle to find the answer. So you got the logic behind what we are going to do, right? We are basically using the cache method. There was no such method earlier, but yeah, there was some cache method, but not exactly for cycles. So basically I've combined two methods, not just two methods, but also I've combined CPU acceleration and other stuff and L1 L2 cache method. So all that combined makes our method much faster than what we can just expect from everyday code. So I've combined multiple methods to create an algorithm, which finally gave me a result. It's just like theorems in math. You first take one theorem and then take second theorem, and then we move to the, and then we combine them to create a third theorem. And suppose if there was some error in this theorem, then what we do is we can basically combine a third theorem with this, which will just remove all the singularities, or you can say all the problems from this theorem. So that's basically what I have done over here. I first tried two things, then more things, and then I kept trying, and finally I got some result which was good and valid. So I published that on Zenodo. So yeah, basically this was the idea behind the research. And now let's talk about these things, explaining minor details of research code. So why did I use I plus plus II, sorry, plus plus I instead of I plus plus? So just tell me one thing. What does I plus plus, and what this does, or what this does? So this is basically equivalent to I plus equals 1, normal thing. So we are not storing this anywhere else, right? We are just directly adding 1 to I. So basically this has to be faster than something that just stores something. It just returns first the original value, and then original value, that means it was stored in some memory. So it took more memory than this, what you can say, this plus plus I. So original I is stored in some cache memory, which is not better than directly using plus plus I. And you already know that I've already taught you why I use signed integers or size t for loops. For loops. For loops. I've already taught you this, but yeah, if I had to tell you again, then you already know the answer, that you don't want to like cause any errors. So we just take all the non-negative values, which is very helpful to us in research. Though it just makes the code a bit slower, you can say. Well, actually, it doesn't make anything slower, because you just have an integer limit set. So limit was set from 0 to the power 30. Okay, so not 32. Actually, for short, I think we have 16. For this, we have 30. Yeah, so it's 32. So for short, we have 16, and for this, we have 32. So for signed integers, we have limit set from 0 to the power 32 minus 1. So this is the limit for signed integers, and for unsigned integers, you already know that we go from to the power minus 31 to the power 31 minus 1. So this is the limit for unsigned integers. So there's nothing that you can do basically in this. Well, next time what I'll be talking about is 0, 1, 2, basically tertiary CPUs in next research, you can say. I'll be making them more efficient than the current ones, but let's leave it for now. I'm currently working on that, but yeah, I can say that I'm very close to like deploying a better algorithm than what we have right now. But yeah, let's talk about this for now. So we have this. Why are we using try? Yeah, so basically, we are using try just for storing data in a simple way. Basically, you already you already know what try does. So it's good for storing these types of data where you have to discontinue something. So try is actually very useful for that. And you also have to use store multiple things. So we can just continue if we have try. But suppose if we don't have try, then we just can't directly continue. We'll just have to traverse again and again. So that's why try is kind of useful. But yeah, so this was all I think about the research. Let's see if there's anything I'm not talking about. Okay, so lexicographical pruning you already know now. Why what it is? Basically, it's like continuing because you already know that it has to be something in increasing order. So we are just exiting from there instead of going back again and again. Next we have edge visits. Okay, so this is also correct. So backtracking is there. Current path.pushback.to, that's also correct. Then we have this explore frontier. Okay, so this is the backtracking. This is the normal tracking. This is current path.popback. Okay. Yeah, so basically this is everything. This is the backtracking thing. This is the backtracking thing. And then we have this as the normal DFS. Basically, whatever. Basically, what you do in DFS, you are doing it over here also. And pruning is already there. If free.to is less than entry node. Basically, what I just told you. Let me just come over here. Basically, if this was greater than 6, then sorry, if 6 is greater than 5, then we just have to continue. Yeah, so this is looking great to me right now. Yeah, so this is perfectly fine. So yeah, so you can just read this proof of correctness. I've already taught you I've already told you the logic behind it. So there's no problem with little bit of walking in the desert. Basically, what I mean by that is you will be no more a traveler. You already know the path, so you are a guide now instead of a traveler, you can say. Anyways, so this is what you can now read, and you will be able to understand everything right now over here. About the complexity analysis, let me just, instead of explaining this again and again, let me just directly run my code over here. Okay, so over here I wanted to tell you something beforehand. Okay, so basically that's not my ID, and that's not my real ID. Basically, I have two IDs on CodeChef and obviously on CodeForces too. On CodeForces, I'm just right at 2247 right now, but yeah, in future I'll be definitely. Also, I'm going to conduct an exam on CodeForces later this month, or maybe in June. So please be prepared for that. All those who have been studying from me. So this is basically raw circuits. These many are there, and these are the filtered try circuits. Basically the lexicographical ones. So let's just take our all circuits and see why only we have got 6. Okay, so over here what we can do is, well, basically you know why we use const. I've already taught you that. It basically makes our code fast. It basically tells, instead of going from memory again and again, copying anything, it just directly runs directly from memory. So it's just a bit faster than usual codes. But right now I'm not worried about going fast. I'm only worried about the result. So what you can do is, for circuit system, there was some all circuits. Yeah, this is over here. All circuits. So basically the main code is over here in this benchmark suite, and this is CSR graph. So basically what I mean by CSR graph is basically I'll be taking a flat array instead of taking 2D arrays, and then from there I'll be just parsing everything. So yeah, so basically if you want something like about this too, a lecture on this too, then I can basically create one on this as well. But for now, we can just think about what we are going to do with the logic. And instead of learning everything in one go, we can just learn everything one by one. So what I have here is for auto circuits to all circuits, uh, we can just for okay. So let me see what I've written over here. Okay, so we have path, the main path. So we'll be traversing in the path dot path, and then we can just see out over here. Then what we can do is we can basically run this. It should give us all the paths. Okay, so I'm sorry, I forgot to write the data type. With auto, we auto capture the data type. Okay, so it was circuit, not circuits. Yeah, so basically this should give us the answer. Let me just comment this out. So I think my internet already went off. Yeah, so it's again reconnecting. I'm so sorry for that. Let's I mean, you can run this by yourself now. You can just check what over here is. Let me just explain the graph right now. So basically we have 1 2 2. Let me just copy this, copy, and then what we can do is we can paste it over here, and then we can increase. Okay, so the size can't be increased, I think. Instead of 11, yeah, so perfect. So in the gist we have 1 2, basically 1 2 2, then 2 to 3, 3 to 1, and then we have 1 to 4, 6 to 4, okay, 6 to 4 and 5 to 6. So we have 5 over here. Okay, so let's make it down instead of going over there. Or maybe if we need 5 3 3 4 4 5. Okay, so 5 should be over here. 5, and then 4 is also connected with 5. 4 to 5, 3 to 4. Okay, so we need 4 over here. Okay, so it's actually much problematic than what I thought it will be. Or we can just do it like this. Instead of going over there, I can create just 4 over. Okay, so 1 is also connected with 4. 1 to 2, 2 to 3, right? And then 3 to 1. We have this 1 to 4, 4 to 5, 4 to 5, 1 2 2 3 3 1 4 5 3 4, 3 to 4. Well, basically I had already drawn this in my real work, but I'm getting some problem right now. This is also done. 5 to 6, and then 6 to 4. Okay, we have 5 to 6, 6 to 4, 5 to 6, 6 to 4, and then 5 to 3. So basically this is our graph. We can actually draw this much better than this, but let's leave it for now. Let's recheck. 1 2 2 3 3 1 1 4 6 4 5 6 4 5 3 4 5 3 3 4 5 3. Yeah, so basically it's perfect. So as you can see, there are multiple cycles over here. So what we can do is we can basically 1 2 3 is a cycle, 1 2 3 and 1. And next we have what is our capacity, by the way? I have written capacity somewhere over here. Okay, so max visits can be 2, the capacity rule. So max visits k equals 2 for now. So we have this over here. Next we can do is 1 4, no, not 1 4, 3 1 okay, so this is also not valid. Okay, so this is valid. 3 1 4 5 3 1, 3 1 4 5 3 1. Basically, if you do it manually, you can just already see that we are having much problem. So that's the reason we wrote that code. So basically in that code, what we are doing is we are just basically normal traversing DFS, and then we are checking if we have already found the cycle. And for cycle rule, you already know we start from 1 and then we go back to that. So if that node is revisited, then we say that cycle has been completed. But in our case, since we can traverse the same node again and again, basically according to the capacity, we have that rule. So we'll be just traversing it as many times as we want. So if that node has been visited once, then it's fine. If it has been visited twice, then it's fine. If it has been visited thrice, then also it's fine. Basically, if it's once, then you already know. Suppose if one is visited only once in this, and we are not getting back at one, then it's a problem. That means it's not a cycle. Basically, it's just 1 2 and 3. So if you want to create it as a cycle, then you have to add 3 to 1, which is over here. So if it's been visited twice or thrice, then we have for capacity equals 2, we have the cycle. And obviously, similar stuff for greater capacity. So that's a simple, a bit, you can say we have changed a bit of logic for DFS, but we can't just do it manually right now. So network is back. So basically all the 29 cycles are over here. Let's first start from the basic one, basically the smallest one. So these are some cycles that we have generated. All of them are lexicographical, by the way. So we have like 1 2 3 1 4 5 6 4 3 4 5 3 1 4 5 3 1 1 2 3 1 and all so on. So suppose these 29 cycles are there, which are non-simple but lexicographical cycles. But suppose if you want non-lexicographical cycles, then obviously you have to just change the logic from here. What we did over here, like instead of cutting the graph, basically instead of 5 plus 6 greater than this, if you don't want the lexicographical, then what you can do is you can basically traverse from some random nodes. Basically you can use for loop, and then you can go in that direction, and you can just remove this if e dot 2 is greater than the max dot dot dot. If it is greater than node, then we continue. We can basically just remove this and you will get whatever you want. But yeah, obviously the time complexity will increase for that too, and you can obviously store that in try still. Basically cache is still working for that. So cache data type, what I mean is basically cache thing is the main thing for this research. So basically try caching is the best thing we can do for graphs, I believe. And later obviously everyone will start using the try caching method after this video at least. So let's talk about the web google.txt, the file which has all the nodes. Basically you can download this from where is the from Stanford one. So basically it says that there are only 875,713 nodes and these many edges, and obviously you have to travel them. And suppose for the normal traversal, what you can do is for every traversal you will need like so basically you can multiply these two and then you can just find the time complexity. So basically that will be much worse than anything. Well, basically you don't have to multiply these two, but yeah, you can find just by these two that how many, if even if it is a simple straight line, then also it will create some problem. So instead of but before that, what I want to say is, what do you think, how many nodes are there in this uh, web graph? So if mathematically speaking, then you can say that all the nodes, suppose you have nodes 1 2 3, 1 2 2 3, and you have 6 7. Oh, let me just write 7 8. Suppose if this is a one index graph, basically the indexes are starting from 1. So what you can say is there are 8 nodes, basically 8 nodes or 9 nodes in case of 9 nodes in case of zero indexed graphs. Sorry, my handwriting is not that good. For zero indexed graphs, and if you talk to some math expert, what he will say is, or he or she will say is, basically they'll say that there are only 1 2 3 4 5 nodes. There are only 5 nodes, because in maths we strictly speak that graph is something which has these two things, vertex and edge, right? So if it doesn't have an edge, then it's not considered a node of the graph. Basically what they mean is, 1 is connected with 2, 2 is connected with 3, 7 is connected with 8. So these can be considered as the part of graph. But if you have only some solo node roaming around, then you don't consider them in the graph. But in computer science, we obviously ignore that, because obviously you don't have any way to write to, like, just do it with that and not travel all these nodes. So why I'm basically speaking this, because in computer science, when you run my code, and suppose you have this, you have downloaded all the things, and suppose you are on my GitHub, then you can go to github guide.txt. Basically what I say is, download the GitHub repository entirely as zip and then extract it, and you can read this. You can basically go from Zenodo. Basically you can go to Zenodo, then what you can do is, you can go to this GitHub link, then you'll be redirected to this Shakti's algorithm stuff, and then you can just click on this github guide.txt, and then you will get what you need over there. So basically you first need to download webgoogle.txt from this website. I've already given the link over here. So, and then you can just follow the instructions to download this. And then after downloading both the things, the zip file and webgoogle.txt, you can just what you can do is move the google.txt file to that folder which you just downloaded and extracted from GitHub. And then what you can do is right click in the folder and then open it in terminal. So if you have Windows, then obviously it will open. If you have Mac, then there are some different commands. So for Mac, I'll be just ignoring it for now, because in Mac you don't have, like, suppose if your Mac has just 8 GB RAM, uh, and then it will be some problem in Mac, because if you just directly want to run this large file, it will basically crash on that. In other RAMs, obviously they're not better in performance if you are doing some single task, but on multiple tasks, or you obviously know that our RAM is good for which we get in Windows. So that's the reason basically why I don't want you to run it on 8 GB Mac. You can basically run this on 16 or 24 GB Mac, but yes, even on Windows you can't run this on 8 GB. But yeah, basically what I mean is, please be careful when you are running this code, otherwise the code will crash and you might blame me for that. So this is what okay, fatal error, no such file or Yes, so we're getting some problem. Let me just first check. Okay, so we do have this, but we're getting some problem. Okay, so it actually created now. I don't know what happened that time. So we can run this. I hope this is how I saved it. Yeah. So basically, as you can see, we have 8, 16, 428 nodes, but over here you can see that there are only 875,713 nodes. So why is there a difference? So basically in our file, as you can see, I've downloaded from there only. There are basically 916425, and if you search 916427, so we have this as well over here. But suppose if you search 8, then you have no results. So basically there are these many nodes, and since our nodes are starting from 0, so we have like all the nodes over there as 916,428. But since there are some nodes as single nodes, so those are not counted in this Google Web Graph. Basically by them it's not counted. I don't know why. But since it's a computer science research, so we can just take mine in account, and we can say that I've done correct stuff, or you can say that what I've done is correct completely. Let me also view my task manager for now, or we don't need this. Yes, basically we have this. So 56% memory has been used. 56%. Okay, so I need to cut some tasks. So basically I'll be closing this Chrome window. Otherwise even I'll be short on memory, because I only have 24 GB RAM. So I'll create some crashes if I don't close this window. So yeah, so I basically have to close this one too. I'll be closing this as well. And if okay, so I can close this for now. So let's wait for some time and I'll be back. Let's keep an eye on this. So I'm just muting my mic, and basically you can just skip to whenever it will be like it will take around 4 minutes, so you can skip 4 minutes later from this. Sorry, not 4 minutes, it will take about 7 minutes, I think. Basically you can check that on YouTube. So let's skip for now. I'm muting my mic, and then I'll be back after some time. Okay, so we are very close to crashing. Basically 78% of our memory has been used. So basically, as you can see in the code, what I have done is basically I'm storing all that try in my memory, so it's just causing few problems. Suppose if graph was something if it had like too big of a cycle, then obviously the memory would have crashed by now. But since Google was kind enough to make small cycles and small, like a small continuous diameter, basically the diameter of the longest, you can say the longest path is basically just, I believe it is 21 or 22, I think. So basically that's our uh, profit right now we have. So that's the positive point. And over here we have, okay, so actually it took just 289.342 seconds. And the total cycles hit were this much, and unique sets filtered were this. Okay, so okay. Uh, well, basically we can just, actually I don't believe that we just solved this in just this many seconds. I also want to check something from my GitHub, so I'll be just restoring all the. So I'll be restoring everything. So we can go to our GitHub and we can go to our README. So basically, last time what I did when I did that, we got. Uh, yeah, so basically it didn't crash out because everything is perfectly fine. We just have 081, and over here also we have 081. But yeah, the time difference is great. So for some reason we okay, so I think in Windows it might have some cache which was stored in there. So when I like tried doing it first, so in Shakti bench, it was like it has a stored few of the graphs, and then afterwards, when I redid this, it just reduced that time. Basically, it continued from there maybe, but since we close the compiler and then we rerun this, it shouldn't have happened like that. But who knows what Windows does behind our, I mean, in the backend. It's just a guess. I don't know whether that's true or not. And about the second thing, it is 661811920. 661811920. Yeah, so it's perfectly correct. So everything is correct for now. So this was basically my research, which I wanted to share with you all. So I might give some questions related to this in our next basically contest, code forces contest. So yeah, obviously if you master this concept, then you will be able to solve that question too. But that is only possible if I give the question in division 1 maybe, because yes, obviously it will create some issue if I just directly give that in division 2. They might make it unrated as they have done like multiple times with many of the contributors. So I think this was it for today. Thank you everyone for listening to me about my research. You can obviously go over here and check what I have done. You can basically select this version 2. Suppose if you want to check the version 1, then you can obviously have this 392 over here. And yeah, so basically that's it for today. Thank you everyone. Thank you for watching and have a good day. Thank you.